Hello, I'm Ray.
And I'm Brian.
And this is Two Skis Walk Into a R, where today we're going to do the ANOVA workflow from start to finish, just so you have it in one wonderful place. What data set are we working with here, Brian?
So today we are going to be working with the IRIS data set. So this is a very old and semi-famous data set that we're going to be working with, which is going to be looking at different measurements of 3 species of iris flower. So we have sepal width and the sepal length, and then we also have petal width and petal length.
Great. Bet you didn't know data sets could be semi-famous.
Semi-famous.
Right. Okay, so what I've already done for you is I have a link for this you're about to see it. Anyway, I went ahead and I downloaded this thing as a comma-separated values, and then I went over to R and I made this data frame object iris.df. I used the read.csv function. Down here in the console, I did file choose to find the path in my particular computer to that CSV file. I pasted it in here. And then I always remember to do strings as factors equals true.
Very important.
Very important. And so we can click on this guy, and you can see that we do indeed have the data set in there. And then it's always a good idea to check the structure of your data set. And so we've got the length, width, these are all numerical, and then look, species is a factor, which is exactly what we want it to be.
You have to make sure that when you're running in ANOVA, that factor designation is actually set, and that's why we did the strings as factors.
Yeah, the strings as factors is what made that be a factor. Cool. Okay, so ANOVA, and now we're going to do, what are we doing? Sepal width?
So we're going to be looking at the sepal width
versus species
of the measurements of the 3 different species.
Okay.
Correct.
Excellent. Okay, so if I go to my famous workflow, we're first going to establish our null and alternative hypotheses. And there's lots of ways to do this, and I'm probably going to kind of mess it up a tiny bit, but our null hypothesis is going to be that
means are going to be equal.
Yeah, that the mean, that at the population level, the mean sepal width, come on, is the same for all 3 species. And then our alternative hypothesis is going to be at the population level, the mean sepal width of at least 1 species is different from the others.
And it's always important to type this out as comments in your R script, because we want to make sure that we have a good understanding of what we're trying to do with our statistical tests.
Yes, thank you. Okay, so this is step 1 territory. Then we're going to do step 2 territory, which is, what is it? Oh yeah, we're going to visualize our data. We're going to use this plot response tilde predictor, and then we always want to put our raw data points on there because then we can see what's actually going on. So step 2, visualize data. Great, so we're going to plot iris.df $sepal width tilde iris.df $species. And then I'm going to go ahead and just copy that stuff. I'm going to click run. There's our data. And then I'm going to do points. And I'm going to paste that same thing in there.
Can you remind us of the difference of the keyboard commands for a Mac and a PC to copy paste?
Oh, yeah. So on a Mac, it's going to be Command C to copy and Command V to paste. On a PC, it's Control C to copy and Control V to paste.
The copy and paste is a friend of ours, so try to get used to those keyboard commands.
Okay, so looking at these, I see that it definitely looks like this species of iris has a higher mean sepal width, at least in this sample. And so the question is, how likely would we be to obtain these data, assuming the null hypothesis that in reality the populations are all the same? So I'm kind of looking at this, Brian, and I'm thinking maybe this is going to be kind of unlikely. I think we might get a small p-value, but we'll see.
We might.
Okay.
This is why we run the stats.
That's why we run the stats. So number 3, we got to create our statistical object, and we're going to include this na.action equals na.exclude. That will make any missing values behave nicely. Okay, so step 3, create statistical object. Okay, and so that I like to call it M. You could call that statistical object anything you like in the whole wide world.
Absolutely.
AOV is our function that's going to create this ANOVA statistical object. I'm going to again paste my response tilde predictor, and then I'm going to do NA action equals NA dot exclude, and now I'm going to click run, and I've created that object. And now to get at that object, we're going to use summary of M, and we're going to see if there's support for our alternative hypothesis.
So how do you know that you ran the object and that it's stored?
Oh, good question. Because I saw it over here in my environment pane, which is a nice thing. Every time I do that, I like to make sure my object exists. Is that how you do it as well, Brian?
That's how I do it.
Nice. Okay, so this is step 4. Get the ANOVA output. Okay, summary of M. Great, let's run that. Okay, and so this is our p-value right here. And so this is telling us that our odds of getting data like this, assuming there's no difference at the population level, is 2 times 10 to the minus 16th. And Brian, it may actually be smaller than that.
It might actually be smaller than that. It's as far as R goes.
Yeah, that's as close to 0 as R can possibly get.
Because we know in statistics you could never have a 0.
Yeah, you could flip a penny 1,000,000 times and get a heads every time. Like, that's possible. It's super unlikely, but it's possible. Right, okay. So this is strong support for the alternative hypothesis that the mean sepal width of at least one of these species is different from the others. Okay, so far so good. Now, if necessary, perform post hoc tests only if the ANOVA is significant and there are more than 2 groups. Well, it is significant, isn't it, Brian?
Strongly significant.
And we have 3 groups, which is more than 2. So it looks like we're going to have to run a post hoc test to say which of these guys are actually different from the others. So let's go ahead and do that. This is going to be step 5, post hoc test. And so one way to do that is the Tukey HSD.
Not turkey.
Not turkey, it's Tukey. And then we're just going to type the little M in there, right? That's the syntax. I'm just going to check.
That's
correct. That's correct. And we'll go ahead and run that. And this is telling me that if you compare versicolor versus setosa, that is a statistically significant difference. That is a very small p-value. Virginica versus setosa, that's also a statistically significant difference. That's way less than 0.05. And then if we check the other two, Virginica versus versicolor, that is also a statistically significant difference. Our p-value there is 0.009 if we round, which is... Yeah, it's lower than 0.05. Your odds of getting those two, assuming they're not actually different, is a little higher, but still really small, right?
And this is a point of confusion for a lot of students, because students will run the Tukey HSD and they will not have the corresponding raw data box plots up at the same time.
Oh, you got to have those raw data
so
box
having
plots.
the raw data box plots is really helpful for your interpretation, because you can then visualize what the Tukey is telling you. Otherwise, it can be a bit of number soup in here and students can get quite confused.
Yeah.
So make sure that you always have the box plot of the model that you ran.
Yep.
That's a very important thing, because a lot of times those box plots can pile up in your R screen. So just make sure that you have the right box plot with the Tukey that you just ran.
Exactly. And speaking of number soup, there's a nicer way to present this. And with 3, species, it's not that big a deal. Like Tukey, like that test is fine. But if you want a prettier output, you can use the Agricole package, which I'm going to just demonstrate here really quick. So I'll need the Agricole package. I have already used the tools and installed it, so I don't need to do that. But I do need to get it into working memory, and the way to do that is with the library function, and we'll do Agricole. That's the one, and then I'm going to run that.
And so I noticed, Ray, that when you start to type as a function, that it kind of filled it in for you.
It did.
How did you get it to actually fill in for you?
I don't know what you even mean.
Oh, because if you don't hit the tab as you go.
Well, on a Mac, if I just hit return. Yeah.
Okay, well, there you go. On a PC, it's a tab.
Okay, you got to tab sometimes. If I had multiple choices, though, I could have tabbed through them.
You could have also tabbed through them.
And selected the one that I wanted. Okay, so let's do this alternative down here. And so this is hsd.test. And you can see it's in the Agricole package because it's showing you right there. And now the syntax here is a little different. First, I want my statistical object M, and then I'm going to take whatever was in the predictor column up here and put it in quotes, like precisely, like whatever was written. And so I'm actually just going to copy it. So Command C because I'm on a Mac, and then I'm going to put some quotes, and then I'm going to paste, Command V. And then there's this additional weird argument that we have to do, console equals true. Console equals
Sometimes
true.
R just likes to be a little finicky.
It does. And now we get this output, which is, to my eyes is a lot prettier, where it's telling us that it says treatments with the same letter are not statistically significant, are not significantly different. But look, these guys all have different letters, A, B, and C. And so that's telling us the same thing that we saw previously, that all of these guys are statistically significantly different from all of the other guys. It's a hard thing for my mouth to say sometimes. Okay, so we did all that. So this is kind of, the data is what the data are, but if we were, iris biologists and we felt like maybe the sepal width should be different, we might be excited. I don't know, but it doesn't matter. We really, we should take the data as they come. We don't want to be tempted into doing any p hacking or trying to coerce our data into significance. That's not a good place to be. So now we've done sort of the quote unquote exciting part, and now we have to do the verify that the p-value is actually valid, because recall that ANOVA has these assumptions that the residuals are normal and that the residuals are homoscedastic, and so we want to do these things. Okay, and so we've got the code right here. First we want to visualize normality. I'm going to do one extra one. I'm going to visualize normality with a histogram, just classic histogram. So now we're to Step 6A, verify that residuals are normally distributed. Okay.
And just remember that you always want to verify your p-value, whether it was significant or not.
Oh, yeah. Because even if it's not significant, you still have to verify that it's not significant.
Yeah, exactly.
Right. That's looking pretty normal to me.
That looks pretty normal to me.
I like that. Okay, and then we have
Bell-shaped curve.
This additional tool of the QQ norm of the residuals of the statistical object and QQ line of the residuals of the statistical object. So we're going to do that. So we're going to do QQ norm. Ooh, that's not how you type. Norm of the residuals.
It's one way to type, Ray.
It's one way to type. There's a lot of ways to type. We're going to run that. Then we're going to do QQ line, then we're going to do residuals of M, and add that line in there. We're not searching for anything. I'm just mistyping. Ooh, that looks beautiful.
That's about as good as it gets.
Yeah, so many of those points are falling on that line. That's looking real good. And then we draw this line in the sand with the Shapiro test. And yeah, recall that here, we'll actually go down. We've got the Shapiro-Wilk test. So the null hypothesis is that data are drawn from a normal distribution, which is kind of what we quote-unquote want. That'll make our lives easier because we probably won't have to transform. And the cutoff is 0.001. The alternative hypothesis is that the data are not drawn from a normal distribution. Okay, so we're going to do...
So you were looking for a value larger than 0.001.
Yeah, you could say that. Yeah, you could say that. Because that's what I'm saying. And I like to put a little comment here. So H0 for this guy is data are normal. That's kind of a sloppy way of saying it. That data are drawn from a normal distribution. And then we'll say we'll kind of conclude that if P is greater than 0.001. And then our alternative hypothesis, our data are not normal. And we'll conclude that if the P is less than 0.001. You agree with that? Does that look right?
I agree with that.
Okay. And so here is the p-value. It's 0.32, which is much greater than 0.001. And so we conclude, we go with the null hypothesis, data are normal. So, hooray, that's fantastic. Very happy about that because, we don't have to get too happy.
You get a little happy.
You get a little happy. Okay, so 6b is verify that residuals are homoscedastic.
And those that are playing at home, it's really important that you are typing all of this stuff out as we go.
Oh, yeah.
And if you need to, hit pause on the video, type it out, and then continue.
Oh, good idea. Good idea. So let's get a visual on this with the plotting of the residuals versus the fitted values. So we're going to do plot residuals of M tilde fitted of M, and then I'm going to run that guy, and ooh, that looks awfully homoscedastic to me.
How can you tell?
Well, the spread of these residuals are pretty consistent. I mean, there's a couple of weirdos out here, but I know there's piles of points on here, and so I think they're looking pretty great. Mm-hmm. But we also have another line in the sand. We can use the Bartlett's test. So we'll use Bartlett's. It's the residuals of M versus the predictor. And again, we have that NA action equals NA exclude, which is going to make everything really nice. Okay, so then we're going to do Bartlett test, residuals of M tilde, and then iris.df $species na.action equals na.exclude. And now,
so what are the hypotheses that we are testing?
Oh yeah, let's do that.
Bartlett?
Oh my gosh, I almost executed without doing that. So data are really drawn from a homoscedastic distribution.
It's a fun word to say.
Yeah, data are homoscedastic. And we'll say we're going to conclude that if P is greater than 0.01. And the alternative hypothesis is that the data are heteroscedastic, which is the opposite of homoscedastic. And we'll conclude that if P is less than 0.01.
And for everyone out there, these are statistical words that are often used in the field, but homoscedastic, just as a reminder, equal variance. So
equal
spread.
Variance. Yeah.
And then heteroscedastic is unequal variance or unequal spread of your residuals.
So these are pretty equal spread, and so probably
homoscedastic.
So I'll be shocked and appalled if. Okay, right.
Oh, also appalled. That's nice.
And appalled, right. So indeed, P here is 0.33, and that's greater than 0.01, and so we have passed that test. And so we pass both of these. The assumptions are met, and the p-value is valid. And the point of it all, what do these results say about the scientific question that motivated the study in the first place? We're a little light on this in the sepal iris.
Science is for science sake. We'll call this a basic science research question.
Okay, great.
Of looking at trying to identify different species by one of the flower measurement structures. So whether that be sepal width, sepal length, petal width.
Yep.
In this particular case, we are looking at the sepal width for these three species.
Yep, and so it looks like they're different.
It looks like they might be different.
Yeah. I mean, there's a chance, it was a fluke, but like the p-value was like, it's practically zero.
And if you look at the dichotomous keys and trying to identify plants, we use these different features to actually separate species out.
See, this is a real life.
So there is some real life activity here to look at
some
of the characteristics to identify which iris you're actually looking at.
Some RLA. Okay. Great. Okay. And we'll do another video that involves transformations.
So can we go back to see what the conclusions are with the data, just to remind ourselves?
We can. I love doing that. Here's the raw data graph. That's what I really like. And then our actual output, which we could run again, is right here. So
we just run it again just so we can easily access all that hard work that we did.
Oh, sure. In fact, I could Control L, which gets rid of everything in the console. I could broom out all of these plots.
That's
a
great way to go.
Broom out all of these objects, and we're just kind of starting from scratch, loading in the data, verifying, yes, we've still got factors here, which is nice. And let's plot it. Oh, there it is, looking real nice.
Visualized data, excellent.
There's our visualized data. We'll create that statistical object. We'll get the summary of that. And so, again, our odds of getting these particular data, assuming that the means at the population level are the same, is really small, which suggests that at the population level, it's actually probably different.
Probably different.
Yeah. I mean, it probably is putting it lightly. Okay, then we have our post-doc output, which is, again, telling us that all of these are different, and we can have that prettier version with the agricole package. Again, giving us the same information. All 3 species appear to have different.
And one thing I like about this agricole package, new to me, I've been doing R for 20 years. I've never seen this package before.
Seriously?
So we're always learning as we go.
Man.
But it's really nice because this output also gives you the means. It looks like a standard deviation.
Yep.
The replication, how many samples were taken for each of our species.
Standard error.
The min value, the max value, and some quartiles, which are the way that box plots are built off of.
Yeah. Love it.
So I've never seen it before, and I will now be using this on my day-to-day life. I'm pretty excited.
Yeah, and when students start doing like 8 different tree species or something like that, pairwise, this test is the normal Tukey HSD version is a nightmare to try and understand, whereas the agricole version is beautiful.
I love it.
Yep. Okay, and then we verified our assumptions, which we already belabored.
We already verified it, but it's important because we now know that we can trust those p-values because we meet the assumptions of the test.
Yes, indeed. Cool. Okay,
That's great.
Let's stop this one and start another one.